start with a PDF file, and I'll be using the whiteboard occasionally. So I'll swap between the presentation and the whiteboard. So essentially, it will be more of like a theoretical class on time series, but I'll try to keep the mathematical element as minimal as possible, and so I hope it would be understandable to everyone. So can you see the shared screen?
Yes,
Can you
sir.
see?
Yes, sir.
Yeah.
Yes, sir. It's
Okay.
visible.
Okay. Okay. So essentially, in today's class, we'll see the introductory time series. It is just like a
Sir,
fast code.
just one question.
Yeah, sure.
Will we get this PowerPoint presentation at the end of the class?
Yeah. Uh, I can share it at the end of the class, but I think it is better if I share it a few days later, because I myself would then like to modify some slides, because I have created it today, but I think some slides may be better written. So would you mind if I share it after the
Yes,
next
yes, sir.
class?
No issues. I just wanted to ask because, uh, or else we will just keep our make our notes.
Yeah,
Okay.
I think you don't need to take notes. I'll share it maybe 1 or 2 days later.
Okay, sir. Okay.
Yeah. Okay. Okay. So essentially, our talk will proceed in the following way. So can you see it in the presentation mode now? Is it moving
Yes, sir.
correctly?
Yes, sir.
Okay. Yeah, now it is full screen, so maybe it is more visible to you. So this will be the part of the time series analysis that I plan to cover in today's class. Essentially, I'll start with some examples of time series and and then we'll discuss about what are the basic objective of time series analysis. Then in the third part of this talk, we'll see what are the exploratory techniques and summary measures associated with time series data. Then in the fourth part of this talk, we'll talk about the statistical models and associated inference. Uh, and then in the final part of the talk, we'll discuss about the forecasting of time series data. So I'll switch to the whiteboard, and I'll show you the mathematical models by writing down the equations in the whiteboard. So if you wish, you can take a screenshot of those whiteboard part, because I don't retain them, but I'll share this slide with you. Okay. But everything that I'll talk about is actually a standard material. So you can also get them from internet. It's nothing very special. Okay, so let us start with the time series data. So what is the time series data? Typically, a time series data is denoted in this form, y t1, y t2, y tn, where yt denotes the measurement value y at time point t. And a very simple example of one such time series data is number of dengue cases registered in some state for 30 consecutive days, 1 to up to 30. And these are the observations y1, y2, y30. So these are some numbers. Like y2 is a number, maybe 50. So that means in the second day, there was 50 registered dengue cases in that state. So such a data set is called a time series data. Uh, Now, what is a unique feature of a time series data, in contrary to the conventional kind of data that we come across, is that in this case, the consecutive observations are correlated with each other. For example, this yt plus 1 is actually positively correlated with yt, which in other way is telling you that the number of dengue cases on the t plus 1th day should be highly correlated with the number of dengue cases on the Tth day, and that is natural. If in some particular day there are a lot of dengue cases is coming, so it is expected in the next day there is a less hope of that less number of patient will be coming, because when there is a high peak in the number of cases, so that will retain for a while. Okay, so we can expect that the next day also will get a very high number of dengue cases. So that means this YT+1, that is very highly positively correlated with YT. So the number of cases on the T+1th day is positively correlated with the number of cases on the Tth day. So this sort of an observation is not visible when we deal with usual kind of data. For example, in a usual kind of data, suppose I'm collecting some biometric measurements on a group of patients, and I'm measuring their blood pressure level. So I never assume that the blood pressure level of one particular patient has something to do with the blood pressure level of another particular patient. So these are like, they doesn't have any correlation. There should not be any correlation. Okay. But this is not the case with time series data, and this is the main difference of time series data with the usual kind of data that we often deal with. So the usual kind of data is also called the frequency data, and time series data is a kind of non-frequency data. So their analysis requires completely different kind of techniques.
Excuse me,
Now,
sir.
yeah, sure.
Sir, in the third point in the dengue example, sir, if
Yeah.
the number of cases in each subsequent days is increasing, then there won't be any decreasing order of
Right,
the...
right. Yeah, yeah, you are absolutely correct. I mean, it's not always true that the number of T and T+1 positively correlated. So it will keep on increasing. It's not really like that. Yeah. So um, when I say it is positively correlated, so I have just used something like most likely. So there is a high chance it is positively correlated, and it is also high, but high doesn't mean it is increasing. You understand? So what I'm telling, suppose today it is 50, then the day after tomorrow it would probably be 45, but it is most likely not only 2 or 3. That is what I'm saying. I'm not saying that today it is 50, it is positively correlated with the number of patients on tomorrow, so it have to be 55. I'm not saying that. I'm saying they are positively correlated. Positive correlation means if today's observation is high, tomorrow's observation is also supposed to be high. Like if today we have seen 50 patient, I'm assuming 50 patient is quite high, which may not be true, but I'm just considering one benchmark that 50 patient means high. So tomorrow I'll see 45 patient. In that case, it is also considered to be. Or tomorrow I see 55 patient, then also it is considered to be. Okay, but high doesn't mean increasing. Okay, high means in a similar level, like today it is 50, tomorrow it is 45, then the after tomorrow is 40. So 45 and 40 are very highly correlated. Then the next day it may be 38. So 40 and 30 are also highly correlated. It is like that. So am I making sense?
Got it, sir. Thank you.
Okay. Okay. So as we have mentioned that the cardinal difference of time series data with the frequency data is that in the time series data the consecutive observations are correlated, whereas in frequency data we don't assume any kind of correlation. We don't assume that the ith patient has anything to do with the I+1th patient, or the third patient has anything to do with the fourth patient or the second patient. Okay, they are completely distinct individual, so there is no reason behind assuming their the value based on them will be correlated. Okay. Now these are some differences of time series data with the frequency data. Firstly, for a frequency data, we don't need to keep the identity of the patients. Like it's like the tagging. I don't need the tag. I just need the numbers. I mean, I just need that there are 2 patients with blood pressure level maybe 180, very high BP, or there are 5 patients with blood pressure level maybe 80, low BP, something like that. But I really don't need the exact name of that patient. Like the name of those 3 patients is Mr. X or Mr. Y or Miss Z. That I don't need. Okay, so I don't need the referencing or the identity of the patients. On the other hand, if you are looking into the time series data, then besides the value of the Y, I also need to keep track of the T1, T2, Tn. So it's like I'm keeping track of the tags. Like uh, uh, it is not enough to consider only the value Y, but I also have to tell you at what point of time T1 you observe the value Y. So it is important to keep the value of Y as well as the value of T1. So both the value as well as the tagging or the referencing is need to be retained for time series data. On the other hand, if you're dealing with frequency data, most of the time, I'm not saying at all the time, but most of the time, you don't need to keep the identity or the ID of the patients. Okay. Yeah, so that is one key difference of frequency data with the time series data. Then in the second difference, which is actually one of the most important difference of time series data, the frequency data, is that yi has no correlation with yj. So by that means that the ith patient, uh, what is the blood pressure level of ith patient, and if I consider the blood pressure level of the jth patient, we don't assume those two variables are correlated or their blood pressure level has any correlation. Okay. On the other hand, if I'm looking into the number of dengue cases on the TIth day, then the number of dengue cases for the TJth day, they might have some significant amount of correlation. They might or might not, I'm not sure, but at least the consecutive days, the data obtained in the consecutive days, they definitely will have some amount of correlation between them. Okay. The third difference between the usual kind of data that we most often deal with and with the time series data is that for the usual kind of data, the technique that we use, those are the t-test, ANOVA model, the usual linear regression or nonlinear regression model, the classification technique. There are different classification technique like logistic regression, then linear discriminant analysis, and many other different classification techniques are there. On the other hand, this sort of classical statistical method are not directly applicable for the time series data. For time series data, you have to do either you have to modify them suitably to create some kind of variation of this classical methods which can incorporate the feature of the time series data, or you have to resort to completely different kind of statistical method. So actually in this particular presentation, we'll talk about completely different kind of methods. And there are methods like unit root test, then ARIMA model, and forecasting method, time series forecasting method. So these are completely different kind of techniques than the well-known statistical method that we almost every time use. Like we almost every time use ANOVA model, regression model, logistic regression, etc., t-test. But those are not directly applicable for time series data. The methods related to time series data are completely different. They are like ARIMA modeling, then forecasting. There are different type of forecasting method, and then there are time series testing procedures like unit root test. Okay. If you have any question, please feel free to stop me. Okay. Now this is one example of a time series data. How a time series data would look like. This is actually a very classical time series data. This is the number of airline passenger throughout the world for each of these months, from starting from the January of 1949 to the month January of 1960. Okay, so this is actually a data for 12 years. and a monthly data for 12 years. So that means 12 months for 12 years. So altogether 144 time point will see the data. So this is a very famous data set, or very, which is demonstrated in almost every basic time series course. And it is called the International Air Passenger Data Set. So as you can see, there is a steady growth in number of airline passenger, monthly count of airline passenger throughout the world. And you can also see there is a seasonal variation in the data. We will talk about these things later, that the steady pattern, the steady growth pattern in this data and the seasonal variation. We'll talk about all these things later. Okay. So this is one example of a time series data. Then this is another example of time series data. So number of daily cases and deaths in India during the COVID time. It's actually the second wave of COVID, which came, I think, around 2021 March, April at that time, I think. Yeah. So this is the number of COVID cases, and this is the number of the death during that period. This is again another kind of time series data. Now in this time series data, unlike the previous data, which has a very clear and steady growth pattern, this doesn't have that kind of a steady growth pattern, but there is a alternating behavior like the previous one. So there is, like in the previous one, there was a up and then down seasonal pattern. So similar kind of pattern is there, but it's not seasonal in nature anymore. But there, definitely there is an alternating pattern, up and down. Then this is yet another yeah. So yeah, right. Epidemic curve can also be considered as a time series data. You are correct. But the thing is that the classical time series model, they may not be suitable for predicting this epidemic curve. Okay. So they may require different kind of models, maybe some kind of non-linear models. But in our course, the kind of model that we'll talk about, the ARMA models, and the SARIMA model, they are called the linear time series model. Okay, so they are actually they works very well in many kind of data sets, but may not be for all data sets. Okay. Then this is yet another time series example of time series data. So this is data. This is a hydrological time series data where the water level for Lena River of Russia, uh, 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 the data have been collected. So this is the monthly water level data set. So I have taken this. I have taken this data set from Technical University of Munich. So you can see there is no steady growth pattern now, but definitely there is a alternating pattern in the water level of the river. And this is expected because there are rainfall and seasonal effects on the river flow. So definitely there is a time where the water level rise, and then there is a time where the water level drops. So there is a seasonal variation is visible from the data. So now let us go into what are the basic objectives of time series analysis. The first objective of time series analysis is to describe the salient feature of the time series data through exploratory analysis and summary measures. So that means in a conventional kind of data set, we often report the mean, the standard deviation, which describe what is the center of the data, or how much variable or how much spread out the data set is around that center. So Similarly, in time series also, we want to report such salient features of time series data through some summary measures. But we'll see that these summary measures are not the kind of summary measure that we work with in the conventional data sets. So they will be a different kind of summary measures. So the first objective of time series analysis is to calculate and report such summary measures. Then, of course, the second step for time series analysis, like any kind of statistical analysis, is to model and do inferential statistics. Like in conventional statistical dataset, you report summary measures like mean, standard deviation, then skewness, etc., etc. But you don't stop there, because uh, then in the next step, you propose some statistical model for your data, and then you carry out inferential statistics. Now, inferential statistics means you perform some test, maybe some t-test or some non-parametric test like Kolmogorov-Smirnov test, and then report the p-value. So just doing exploratory analysis and just reporting descriptive measure won't help you much, because this uh, exploratory analysis or descriptive measure, they will just tell you some value, some numbers, but they don't tell you how much reliable those numbers are. Or as we have discussed this in one of the previous occasion, that whatever you are finding in your sample, you need to translate it back to the population level, because that is the actual objective. Your actual objective is to study the population, but since the population is very large and you cannot get hold of everybody in the population, so you pick up a representative sample and study it, report some number, and then try to translate back that number, that finding, to the population level. Now, if you just do descriptive statistics, if you just do the descriptive statistics, then the problem is that you can only calculate some numbers, but there is no way of knowing how reliably you can translate those numbers to the population level. For that, you will need some statistical significance level, like some p-value or some confidence interval, that kind of measure. Now, that kind of measure is only possible when you assume some statistical model or some probability model, like you assume normal distribution or other kind of distribution, Poisson distribution. So similarly, also for time series data, at the first step, you can calculate certain summary measures, but that doesn't lead you to very far. If you want to report some statistical significance, or if you want to translate your finding to the population level, then definitely you will need some statistical model. So the second step, or the one of the second objective of time series data analysis, is to propose such suitable model for time series data. Now, these models will be different than the kind of statistical model that we work with for the ordinary or conventional kind of data, like the normal distribution or the Poisson distribution. This will be slightly different. We'll see that later. Now, once we get hold of such appropriate model for the time series data, the next step is do inferential statistics with those models. Just like in the conventional statistical data set, you assume normal distribution and then you perform inferential statistics using t-test. Or suppose from the data, it looks like it is not normally distributed. Then what you do, you don't assume normal distribution, but you assume something more general, and under the general assumption, you are no longer able to carry out the t-test, but you have to then work with perhaps with the Kolmogorov-Smirnov test, the non-parametric test. So similarly, also in the time series setup, you specify the model, and then under that particular specification, you carry out some inferential statistics. That inferential statistics may be finding some coefficients, or maybe doing some testing, and of course interpreting the findings of those inferential procedure, like interpreting the p-values or interpreting the estimated value. The most important objective of time series analysis is to do forecasting. Like, it is basically, based on the data you have obtained so far, you want to see what would happen in near future or in far future. But in generally, forecasting in far future is very difficult. It's very challenging and very difficult. And truly speaking, there are not very good models which can be used to predict very far future. That is actually not possible. Okay. On the other hand, the kind of statistical model or the time series model that I'll be talking about in today's class, they are actually very good for short-term forecasting. So, in generally, uh, if we want to predict the short-term future, we call it short-term forecasting. On the other hand, if you want to predict very far ahead in future, those are called long-term forecasting. Now, long-term forecasting is very difficult. You can understand like what is happening today. Based on that, if you want to predict what would happen after 10 years, it would be very difficult. Like there will be a lot of uncontrollable factors between playing their roles between this large span of time. And so whatever good method you use, your forecasting may produce completely wrong result. On the other hand, if you want to use, if you want to do short-term forecasting, that is possible. And the kind of statistical model that I'll be talking about in this class, or maybe you are aware of, like the ARMA model, ARIMA model, those are actually quite good for short-term forecasting. But forecasting is actually the most important part of time series analysis. And then the last, another objective, but won't be considering this objective in this course. So that is the calibrating or reverse engineering a time dependent system to get the desired output in future. So it's like I'm looking into a time series data uh, in a uh, in a factory environment, and I have a predefined level within which I want to see the time series. Okay. Now, suppose I see that the time series is actually deviating from that pre-specified level, then I have to think of how I can calibrate the starting point so that uh, the after a while my time series will fall within the that specified level. So this is called actually this is called the control problem in time series, and this is a different kind of problem, but this is also part of time series analysis. But uh, in our course we won't be considering this objective of time series analysis. So essentially in this course we'll be talking about the first objective, that means calculating the summary measure. Then the second objective, proposing appropriate statistical model for time series data and carrying out inferential statistics under them. And then the third objective, so doing forecasting, short-term forecasting, essentially using those statistical models. Okay. So yeah.
So regarding the last point,
Yeah.
The calibrated time dependent system to get a desired output. If we don't get any desired output, so we have to calibrate in the initial point. But the
Right.
initial point which was already in there, that is the fixed.
Yeah.
So how can we calibrate that?
Right. Right. Yeah. So that the thing is that it's may not be applicable for the kind of data we are talking about. Okay, it is applicable maybe in a factory situation. Suppose if you calibrate a particular machine to a particular starting point, and then after one day it will reach to a position. Now suppose you see after one day you see that the position uh, is it's actually fall outside of the specified level that you want to achieve. Then what you can do, you can do some calculation based on time series analysis, and you can find, it's like, for example, I'm just giving you maybe a very naive kind of example. Suppose my initial starting point was 10, and then I observed that the uh, after running the machine or the process for whole one day, I am getting an output like 50, but I want an output between 30 to 40. Then what I can do, I can calibrate the initial value 10 to 0, so that after waiting another day, if I restart my system, it will, after 1 day, it will reach to the position 40. So am I making sense? So I'm telling it in this way. But it is definitely not applicable for the kind of time series that I have shown you, like the number of dengue cases. So those are not something which I can control.
Okay, sir.
Yeah, so these are the time dependent system which is generally studied under the framework called control system. Actually, engineers, they study these things. Okay, but these are actually slightly different than the kind of time series we deal with. We deal with time series which comes as a part of observational study. Like, we are observing the state of nature, and there is no way we can control the starting point of the nature. So that is beyond our control. So it is something like that. But the kind of system that I am talking about in the fourth part, those are essentially machine generated objects. So there you can always calibrate it. So that's the difference. And that's why actually I'm not going to consider this in this course, because their theory is slightly different. But still, they are also part of time series analysis.
Got it, sir.
Okay. Yeah. So now let us talk about the summary measures, the basic summary measures associated with time series data. Now, before proceeding further, I just want to tell you one thing, that although I have told you that I am working with time series data YT1, Y2, T2, YTN, but in this course, I'll be always assuming that this T1, T2, TNs are equispaced. By that, I am meaning that as if I am keeping record on day 1, then day 2, then day 3, and so on. Or maybe on month 1, then the second month, then the third month, and so on. So there is a equal gap between the consecutive time points. Now, what happened in certain kind of time series data, you don't have this luxury. The data comes to you with unequispaced time interval. Now, their time series analysis will be different. So those are called the unequispaced time series data, and their analysis would be different. I'm not going to talk about this time, that kind of time series analysis in this course. Their modeling is also different. Their approach is also different. In this course, we'll be always talking about time series where this T1, T2, Tn are equispaced, or they lie on a regular grid or regular interval, like first month, second month, third month, or first year, second year, third year, like that. So it's not uh, erratically spaced, like 1 day and then after 5 days and then after 2 days. It's not like that. If you come up with such a data set, the model that I'll be talking about, they won't be applicable to such data. So there are different model for such time series, non-equispaced time series data. So in our course, we'll be always talking about, or we'll always implicitly will assume that the time series data is equispaced. Okay. Okay, so conventional summary measures like mean, median, standard deviation, these are not useful. So let us go back and see. Now, suppose this is an example of a time series data. Now, if you look into the conventional summary measures like mean, what you will see that actually these are not really in absolute number. I think these are 100 times maybe 1000, something like that. So that scaling is not present in the picture. So let us assume that there are 100 people on January 49, and then around this region you will see there are 600 people. So essentially these are the data points and some numbers spanning from 100 to 600, and if you take their average, you will get some value around maybe 350 or so, 350, 400 or 300, something like that. But that really doesn't have any special significance. So that is a key difference. Like, when I talk about the blood pressure level of some patients, then it is meaningful to calculate their uh, average or arithmetic mean. On the other hand, if I give you a time series data of number of airline passenger, if you just add those values and divide it by, since I told you that there are 144 data points here, 12 months for 12 years, so altogether 144 data points. So if you just add up all those 144 numbers and then divide it by 144, what you'll be getting? You'll be getting some number around 350. That doesn't have any meaning. Okay. So that's a difference, that the conventional kind of summary statistic like mean, median, standard deviation, those are not, those are, those doesn't have any meaning in the time series data. You can of course calculate them. You can of course calculate them, but they doesn't have any meaning. So there is no real interpretation of them. So that's why uh, I told you that the summary statistic that we derive for the usual kind of data, they doesn't suffice for time series data. For time series data, we'll be needing completely different kind of summary measures, and strangely, which are not even some summary measures in the form of numbers, but summary measure in the form of functions. I'll describe it. What do I mean by that? So one such summary measure is the trend or the trend function. So what do I mean by trend function? By trend function, I mean the long-term smooth behavior of the time series. Then another summary measure is the seasonal component function or the seasonal component part, which is also denoted by ST. Like a function of time is denoted by FT. You know, this is a conventional notation, FT. We denote when we try to present a function of time, we denote it by FT. Similarly, we just, since I want to represent the trend as a function of time, I represent it by the formula T of T. Similarly, we can also talk about the S of T, which is the seasonal component. This is also another function. And this function actually depicts the periodic behavior of the time series data. And then there comes the irregular component part or the irregular component function, which is the leftover after we remove the trend and seasonal component from the data. Okay. So these are the basic summary measures for the timing that we'll be talking about for the timing. We'll see another very important, not actually one, but two more very important summary measure later. Okay. So let us see, what do I mean by a trend? So this is an example of a time series data. So can you see that uh, if I talk about what is the long-term smooth behavior of the trend, so I can draw a straight line, and that straight line gives me a long-term smooth behavior. So this is basically the trend. Okay, is it okay? Is
Yes,
it
sir. Yes, sir.
okay? Okay. So let me explain you something right now in the whiteboard. All of you can see the whiteboard, right?
Yes, sir.
Now suppose I can also say that this is a function which give me the long-term smooth behavior of the time series. No, this is giving me the long terms, not giving me. Okay, I think the whiteboard is gone. Suppose these are the data points. Okay. And now suppose I come up with this. But this is really not a smooth behavior. Okay. Because there are lot of ups and downs. You can see it, right? So, or maybe I can do better. Suppose I just write down such a function passing through the data points. Suppose I'm passing, I'm drawing such a curve through the data points, and you can see that this is depicting the behavior of the time series, but this is not a long-term smooth behavior, because if you consider in long term, you'll see there is lot of ups and down in the curve. So it is not a smooth behavior. Do you understand that why it cannot be a trend function? Because if you think of it in a long term, I mean, if you think of it in short term manner, suppose if you consider it within a very short span of time, then definitely if you magnify it, it would look like something nice and something very smooth. But if you think of it in a long term manner, maybe within this whole width of time, then there are lots of ups and downs. So it is no longer a smooth behavior. A smooth behavior means there should not be too much ups and downs. So this is definitely not a trend function. Okay. However, this is a trend function because this is depicting the long-term behavior of the time series as well as this is smooth. So that's why this is a trend function. Now, someone may also say, okay, this is also a trend function. Yes, this is also a trend function. So when I say trend function, I don't fix anything. I mean, it is also very flexible. Like when I ask you, can you give me a representative value of the data in the conventional kind of statistical data? So what you do, generally you calculate the average. Now there can be some people who may come up with, instead of calculating the mean or the average, they may like to report the median. So both are equally good. Like if someone is proposing mean as a center of the data set, or someone is proposing median as a center of the data set, both are equally good. Both of them have certain advantages over one another under certain scenarios, but at least in a well-behaved data set, both mean and median will work well. Similarly, also in the time series analysis, now if there is a possibility that for this particular data set, someone may come up with a linear trend, like this red line, which is a linear trend or a straight line, or someone may come up with the blue line, which is a quadratic function, like a function of the form y is equal to at plus at square plus bt plus c, that kind of a function. These sort of functions are called quadratic function. So that kind of a function, gt function. So someone may propose a quadratic trend, or someone may propose a linear trend if t is equal to mt plus c. So this is the linear trend and this is the quadratic trend. It completely depends on you whether you want to work with a linear trend or you want to work with a quadratic trend. Now, there are situations where the data is distributed in such a manner that just by looking into the data, it is absolutely clear that it cannot be a linear trend. Like there is an up and then down. Suppose your time series is like there is an up and then there is a down. So if your time series is like that, then definitely a linear function won't suffice, because a linear function can only grow or it can only going down. But there is no going up and then going down. That is only possible if you are working with such a quadratic function. So in that kind of a time series data set, definitely the linear function is not going to give you a valid trend, but then the quadratic function will give you a valid trend. So that means in many occasions, different people may come up with different trend, but that doesn't mean their result is incorrect, or there's a possibility both of them are actually giving equally good result. Like if two people, one of them propose mean and another one is talking about median, so it may happen that both are equally good. So similarly also time series analysis, you may come up with your own trend function, someone else may come up with his or her own trend function, and both may be equally good. So that is possible. Okay.
Sir, I have a question.
Yeah.
Like as you have mentioned that if the time series goes up and down,
Right.
then I have to come with the quadratic function. That doesn't that necessarily means that I cannot come with a straight. It is not the
Straight line.
straight line.
Right, right. It
So,
cannot be a straight line.
how can someone with come up there? I mean, how can the two be same?
In that case, it cannot be same. In that case, the linear function is not going to work. In that case, only the quadratic function will work.
So,
Right. Okay. So just let me show you a picture. So it happens in many agricultural experiment that if you increase the amount of fertilizer and if you calculate the yields for different levels of fertilizer, and that also, this kind of experiment also can take place in medical setup, where you increase the dose of some particular medication and see the response on the patient. So what would happen, there will be some particular point where it will reach the optimal level, and then if you increase the dose, the condition no longer improve but it deteriorates. So in that case, the time series data, I mean, although it's no longer a time series data, but that kind of a pattern can also be observed in a time series context. So suppose you are observing in particular for a particular time series data that it is increasing with time and then decreasing. Now in that case, there is no way you can propose a linear trend, right? So if you try to propose a linear trend, it would look like this. So it won't actually capture the data well. So in that case, linear trend is not suitable. So you have to work with a quadratic trend. Is it okay?
yes, sir. If you explain us with some more examples, it will be better.
Okay. Suppose if you see the for example, suppose if you see the number of sales of EV maybe in Indian market, you'll see that when the concept of EV first came, and then there was lot of proposal at the government level that eventually within 2030 every car will be replaced by EVs in India, and there was a lot of optimistic statements from the government itself. So at that time, the number of EVs produced by companies and sold by companies, that goes up, but later on it goes down, because then later on people realize that although we are talking about EVs, but we still don't have that kind of an infrastructure. A lot of issues with battery charging stations of EVs being available everywhere. So now the number of production of EV cars is going down. So if you see such a data set for the number of EVs produced by companies, different companies, you'll see that has an increasing pattern, and then there is a decreasing pattern. Now suppose if you want to calculate the trend curve for such a data set, definitely it have to be of the form like this, and definitely the equation have to be of the form this. So it can never be of this form. Sorry, it can never be of the form of this form. This is not possible. So that is what I'm telling. So is it now okay?
No.
So what I am suggesting that there would be occasions where both a linear function as well as a quadratic function, they will work well. Like there are data sets where if you work with mean or if you work with median, both work well. Now there are situations where if you want to work with median, it may not give you correct answer. You have to work with mean. Now similarly here also there is a possibility that there are certain kind of data set, time series data set, where if you want to work with the linear function, it is not sufficient. You have to work with a quadratic function. Am I now making sense? Is it now understandable to everyone?
Yes, sir.
Okay. So actually there can be something more also, like your data may have this kind of a pattern, that there's a up down, and then there is a up. Now in that case, so can someone from you suggest me what kind of a trend curve would be appropriate in this case? So previously I was saying that there is a up and then down, so I was working with the quadratic function. Now there is a up and then down and then again up. So for such data set, what kind of a function would be appropriate? What do you think?
Quadratic.
No, quadratic won't suffice, because if you try to, now the behavior of the quadratic is that it will go up and then go down forever. It can again turn back. So if you really want it to turn back, you have to work with such a function in that case. That kind of function. So basically you are working with now a cubic function. So based on the
function?
What?
Sine function?
No, the sine function has a problem that sine function goes up, then down, then goes up, then again goes down, like that. So it is actually suitable for periodic behavior. But suppose your data is like that, it is going up, then going down, and then going up forever, then sine function is not suitable. Then you have to work with a cubic function. Okay. So that means it is actually based on your observation, you have to decide what could be an appropriate trend function. Okay, and there is no such hard and fast rule that this is the trend function and only this is the correct, and someone if come up with a different trend function, that is incorrect. There is no such hard and fast rule. The only thing is that in some situations one trend function is more appropriate than the other. So you just have to take care of that. Okay. Let us again go back to our presentation. Yeah. So in this case, you can see that we have worked with the linear trend function. Okay. So for this particular data set, a linear trend function depicts the long-term smooth behavior of the time series quite well. So in this case, it is enough to work with a linear trend. Okay. Now the question is, how do we determine the trend function? Firstly, see that looking into there are two different approach. One method is method of mathematical curve fitting. The first method is method of mathematical curve fitting. So in this first method, firstly looking into the picture, you decide about the form of the function. So you decide whether it is a linear function. That means whether it is a function with the equation a plus bt, or if it is a function with the formula a plus bt plus ct square, or something else, maybe some more complicated function. So firstly, you have to decide on that, and that is a subjective decision. Okay. So what should be the form of the mathematical curve? Now, once you have decided on your form of the equation, like once you have decided that it is of the form a plus bt plus ct square, or it is of the form a plus bt, then the next thing is to determine this unknown coefficients ABCs. Note that these ABCs are not known to you. I mean, if I change the value of AB, the straight line will change. Okay. So how to get this particular value of AB that I'm getting in this picture? So of course you can use the software. We'll see that later in the next class, that how to use the software to get this A plus BT, A value and the B value. So firstly, you have to decide the form of the trend curve. That decision you have to take yourself. And then in the next step, you try to determine the value of this unknown coefficient. Now, that part can be done using the software. So you will use either Jamovi or SPSS or whatever software you like, or RStudio. You just give the command, or you just click on that, and that will give you the value of this A, B, C. It's like that. So that way you get the trend function. So the question was that how to determine the trend function. Now using those values, you will get some, maybe in this case, you will get a value like 2 plus 3t. Then if you plot the function 2 plus 3t on a graph paper, and if you overlay that on the original data set, it should look like this. Okay. So this is one method of determining trend function. Now there is another method of determining trend function. So this is called the moving average method. And in this case, actually, we calculate rolling weighted averages of the time series. I'll explain what do I mean by that. Okay, so the moving average method, what do I mean by that? I'll explain. Suppose this is my time series data. So how do I calculate the trend function for moving average method? So one method is, suppose I'm considering moving average of order 3. In that case, what I'll do, I'll take this, and these three values. So that means the first day, the number of patient on the second day, and the number of patient on the third day. I'll just take their average. So after taking their average, I'll get some value. Suppose I plot that value here. Then I take the value of the second day, third day, fourth day, and I take their average. That will again give me another value. So I'll plot it here. Then I take the value for the third day, fourth day, fifth day. I'll take this 3 value, and I'll calculate the average of those 3 value. Again, I'll get some number like that. So in this way, I'll keep on getting certain numbers, and this number will actually give me a trend function. So this method is called moving average. Why? It is like you are taking a rolling window of size 3, and you are moving that window and keep on calculating simple arithmetic mean or simple average of the data points and just telling those averages to be the train function. So this is another method. Now I'm talking about a moving average method of order 3. You can definitely work with a moving average method of order 5. Okay. But the problem with this approach is that for the initial data points and the terminal data points, you won't get any value of the train function. For example, if I want to get a train value for the first day, I cannot get it, because for getting a train value of the first day, I should have the data for the day before first day, for the first day and the second day, because I'm taking the average of 3 numbers. But the data for the day before the first day is not available to us. So I cannot calculate that average. So I cannot calculate the train function for the first day. So this is the limitation of this approach, that if you use this moving average approach, a few data points for the first few data points and the last few data points, you cannot get any value. Now, in this case, we are working with 3-point moving average. If we are working with 5-point moving average, then the situation is even more worse, that I cannot get the value for the first 2 data point, the train value for the first 2 data point. I can only get the train value for the 3rd data point onwards. Similarly, at the terminal level also, I cannot get the value of the train function for the very last and the last 2 data points. For them, I cannot get any train value. So this is the limitation of this moving average method. Is the moving average method clear to everyone? It is just like you are taking the values for the first day, second day, third day, and taking their averages, and you are assigning that number as the train value for the second day, and so on. So is it now okay?
Can you please repeat once again the last
Yeah.
question?
Okay. See how I am calculating the moving average in this case. Suppose I want to calculate the train function for the second day. Then what I'll do, I'll take the data for the first day, data for the second day, and the data for the third day. I'll add them up and then I'll divide them by 3. That will give me a number. So I'll call that number as the train function for second day, and I'll put it there. Similarly, I'll take this number, the second day, the third day, and fourth day, and I'll calculate their average. That will again give me another number. I'll put it here, and so on. I'll keep on doing this. Now, these numbers will give me the train function. So this is called the moving average method, because I'm calculating the average of 3 numbers, but at the same time, I'm moving forward. Like initially, I was calculating the average of 1, 2, 3, the first 3 days. Then I was calculating the average of second day, third day, fourth day. Then I'm calculating the average of third day, fourth day, fifth day, and so on. So that's why it is like I'm calculating an average, but with a rolling window. The window of size 3, and the window is moving. So that's why it is called moving average. Is it okay?
Yes, sir.
Sir, if the rolling window is 5, then we can take the average of 5.
If the ruling so what is your question?
It means the rolling window is 5. Then we
Yeah.
have to take the average of the first 5 days. Then it is
Right. Absolutely correct. Average of the first 5 values then.
And sir, it is for the 4th day or 5th day or first day or second day.
Right. First, second, third, fourth, fifth. You calculate the average, and you have to put that average on the third day. So that would be the train value for the third day. So that's what I
Why
have
third?
to.
Why not second, sir?
You cannot do that, because you are taking average of 5 days, and that have to be put in the middle point. So you are taking average of day 1, day 2, day 3, day 4, day 5. If you calculate their average, that average should be assigned to the middle time, right? And the middle time is third day. So that's why you have
But
to do
that
that.
means the ruling window should always be the odd number.
No, it can also be even number, right? It is actually a very interesting question that why I am talking about the rolling window of odd number, because the rolling window of even number is also possible, but then there is a problem that suppose you take the rolling window of size 4, like day 1, day 2, day 3, day 4, and you calculate the average of this 4 number. Then where you have to assign? You have to assign it in the midway. Now midway means you have to assign it at the 2.5 day. So the middle point between 2 and 5. 2 and 3, sorry. Yeah, 2 and 3.
Hmm.
And similarly, you'll calculate the next average for the next rolling window. It will be placed between 3 and 4 and so on. So now you got some values at 2.5, 3.5, 4.5 and so on. Then what you do, you in the next step, you apply a 2-point rolling average. Like you calculate the rolling average of uh, the derived values. Now the derived value means some values at 2.5 and 3.5. What would be their rolling averages? Now you take the value at 2.5 and you take the value at 3.5, the trend values, you add them up and divide it by 2. So now you can place it between 2.5 and 3.5, which is 3. Now it become okay. So that is the problem of using even window size for rolling averages. Now, if you want to work with a even window size for rolling averages, you have to apply the method 2 times. Firstly, you have to apply a rolling window of size 4, and then you have to apply another rolling window of size 2. Or at the first step, you have to apply a rolling window of size 6. In the next step, you have to apply another rolling window of size 2. So like that. So that's why it is better not to work with even window averages, because you have to apply the procedure 2 times. It will unnecessarily complicate up things. So that's why I avoided it, but it can be done. Is it now clear?
Sir?
Okay, sir.
Yeah.
Sir, how can this ruling window be decided?
Yeah. So actually, that is like I mean, you have to try out different rolling window. Now, if you take your window size very high, what would happen? Actually, this is very interesting question, that how do we decide that should I work with a 3-point rolling average or 5-point or 7-point or 9-point? I mean, if you take too large window, what would happen? The train function would become very smooth. I mean, too smooth like that. It is not good. On the other hand, if you take your window size too small, like suppose you are taking only one window of length 1, so that means you are taking the data itself and just putting that value, then your train function will be passing through the data points and it would be too rough. So there is a trade-off. That means if you make your window size very small, the train function will become rough, and we generally don't want to work with rough function, because rough functions, their behavior is unpredictable. On the other hand, if you make your window size very large, it becomes too smooth. That means all the interesting information got lost. You are sort of over smoothing the data. So you have to settle somewhere in between. Now, what is that in between point? That you have to decide on on yourself. I mean, you have to try out different values. Okay, it's like that.
Yes, sir.
Okay, so I think someone is asking some question. So yeah, so anybody have any other question in this regard?
Sir, can you give a practical example while deciding upon the rolling average? Like the previous student had asked a very valid question regarding how the rolling average is decided. For example, in my institute, one of the faculty published a paper using ARIMA time series model to determine the cancer. He predicted the cancer mortality, sir. So can you give us some real examples, sir? How? Because right now this is understood, sir, the way you are explaining.
Hmm.
But how in real life these while
You are talking about ARIMA model, right?
yes sir, yes
Auto-recursive
sir.
iteration. No, that order, the moving average that appears in the ARIMA and the moving average we are talking about, those are different.
Okay, sir. No, I mean, can you also demonstrate, or can you give a from a real world experience, sir, how these moving averages can be determined? Uh,
Yeah, I'll talk about that, right? I'll talk about that this on this class itself, and also I'll talk about that in the practical hands-on training class. That how do we decide on the order of the moving average? I understand that you are talking about the ARIMA model, and in ARIMA model there are parameters called PDQ, and there the Q decides the size of the MA. Now, your question is how do we decide that Q value, right? So there are
yes, sir.
there are concrete technique for deciding that. There are statistical technique for deciding that. We'll talk about that later. But right now I am talking about moving average. So actually this is also a very interesting question and important question, because here I am talking about moving average method for trend estimation. And what he is asking, it is called the moving average process or moving average model. So although the name is very similar, those are actually different objects. The moving average model comes when we talk about the inferential statistics. We'll talk about that later. Is it okay?
Yes, sir. Yes, sir. Okay, sir.
Yeah. So the question you are asking, that is actually related to ARIMA model, which is a different thing. That MA part in the ARIMA, that is also called moving average, but that has nothing to do with the moving average we are talking now. So you will see that later. So the equation look very similar. That's why the name is also similar, but the object is different. And there are actually concrete method for deciding the size of the MA. There are formulas, statistical formulas. Okay. Okay, so let us go back to the presentation. Okay, so that means there are two different methods for determining the trend function. One is the mathematical curve fitting method, where you visually uh, inspect the time series data. From there, you guess some mathematical equation. Now that guess part depends on your experience, like whether it is better to work with a linear function, or it is better to work with a quadratic function, or if it is better to work with a cubic function. So it is purely subjective judgment, matter of subjective judgment and experience dealing with that kind of data. Now in the second step, there you don't have to decide about the form of the equation, but now you have to decide about the size of the rolling window. So in both cases, you have to make some subjective judgment, and it may not be the case that all the time you are coming up with the best possible judgment. Okay, so I mean, there is no hard and fast rule like this is the best possible equation for trend, or this is the best possible size of the rolling window. Okay, there is no such hard and fast rule. You have to try out different equation and then decide which one is giving you the best result. It's like that. Okay. Okay. Now let us see what are the distinctions between these two approach for trend determination. The first case, uh, we are having now a global formula that can be used to forecast. So what do I mean by that? I have a form. So yeah, I'll explain that later in the whiteboard. However, the problem of mathematical curve fitting is that it is unable to capture sudden changes in the time series. So that means it's not very flexible, or it is not very adaptive in nature. So it may happen that your time series was showing some kind of behavior up to certain point of time, and then suppose some drastic measure like a lockdown was imposed. So from that day onwards, or maybe after everything takes place properly, or the effect is revealed on the number of patients, you'll see there will be a sudden change in the number of patients. Okay, so such sudden changes are not very well captured if you use method of mathematical curve fitting. On the contrary to that, if you use the moving average method, it is very flexible. It's local in nature. That's why it is very adaptive to sudden changes. But then definitely it will also have some disadvantage. Now that disadvantage is that it doesn't give you any global formula, except if you are working with one-sided moving average. There is a concept of one-sided moving average. We are not going to talk about that. But the kind of moving average I was talking about, for them, you cannot get a global formula to do forecasting. Let me explain what do I mean by that. Okay. Suppose your time series data was given like this, and then you fit a trend curve. It looks like that. Now suppose suddenly after this point of time, your time series data is changing. But again, if you fit a new trend curve to after this additional data you are able to procure, your trend curve will still shift a little bit, but still it would be kind of behaving very rigidly. It will try to retain its original shape. It's not very flexible to that change. On the other hand, if you are using a moving average method, you'll see, I'll show you a graph of moving average later. You'll see your trend will be like this, and then suppose suddenly your time series got changed, then you'll see the moving average trend is also changing. So that means moving average is very flexible. Compared to the method of mathematical curve fitting, the moving average method gives you flexible result, because moving average is a local method. Like you have a rolling window and you are not considering any data outside of that small window. So that's why it is a local method. It only involves the adjacent data points. So since it is a local method, it is very flexible and it is very adaptive in nature. So if there is a sudden change in your time series pattern, it will be captured by the moving average method, but that won't be captured by the method of mathematical curve fitting. So that was the that is the advantage of method of mathematical curve fitting, and the sorry, that is the disadvantage of method of mathematical curve fitting, but the advantage of moving average method. On the contrary, moving average method has a problem that if you try to do forecasting, suppose you got the time series data up to this point. Now, if you want to forecast for next 10 days, suppose you want to forecast for next 10 days, will you be able to forecast? It is not possible, because see that if you want to forecast for this particular point for a using a 5-point moving average, what will be needing? You'll be needing the data for this day. You'll be needing data for this day. You'll be needing data for this day. You will be needing data for this day. You'll be needing data for this day. Unfortunately, data for this day, data for this day, data for this day, these are not available to you. So how can you apply that? So you cannot do forecasting. So that is a problem. That is a problem of moving average, that it doesn't give you any formula like a plus bt or a plus bt plus ct squared. It doesn't give you any formula. It just give you some numbers and you don't get any formula. So that's the problem of the moving average method, that you cannot directly use to do forecasting, which is the prime objective of doing time series analysis. So this is a problem. On the other hand, if you are using method of mathematical curve fitting, what would happen? You'll get such a trend curve, and based on that trend curve, you can forecast. The forecast values may not be great, but still you can do forecast. So what will be your forecast value? Suppose for the next day, this will be the forecasted value. Then the day after that day, this will be the forecasted value. Then day after that day, it will be the forecasted value. It will be forecasted value, and this. So you can keep on doing forecasting. Of course, the forecast won't be good because you'll see that your time series is actually going down. Whereas since this method of mathematical curve fitting are not very flexible, it is retaining its original position, and that's why the forecasted value and the value you most likely going to get, there will be large differences between them. So of course, it's not don't give you good forecast, but at least you are able to do some forecasting. And while for the case of moving average method, you are not even able to do any kind of forecasting. So that is the problem of moving average method. Although it is very flexible, it is very adaptive. It don't give you any formula, global formula directly. Okay. Is it okay? Is it clear to all of you that what are the advantages and disadvantages of both this method?
Yes, sir.
Okay. So again, go back to our presentation then. So these are some of the differences of yeah. Now see that here I have shown the method of mathematical curve fitting and moving average method for the same data set in two windows side by side. For the first cases, this is the air passenger data, and I have fitted a quadratic trend, and it is actually giving a good fit to the data. In the second case, I have fitted a 3-point moving average to that same air passenger data, and this will also give me a very good trend equation. So both of them will actually give me good trend equation. Can you see the two pictures? Is it appearing to be very small in your screen actually, or you are able to see the differences, the red lines? Okay.
So,
yeah.
So if I understand correctly, in the previous slide on the left side, that looks like the right one looks like the one in which the moving average was rolling moving
Right.
average was taken.
Right.
And in the left was the one in which the mathematical curve method was used.
Right.
So,
Right.
because it is following some kind of a fixed trajectory, sir.
Right. That's why we use the term global every time. I mean,
Beg your pardon, sir? Beg your pardon, sir?
Right. So that's why we are repeatedly using the word global. So it's like a fixed thing. I mean, it doesn't change with time. On the other hand, the moving average is local in nature. So that's why we are using that term local for moving average. And whenever I was referring to method of mathematical curve fitting, I was using the term global.
Yes, sir. Now understood, sir.
Yeah. Okay.
Sir,
yeah.
So in the previous slide,
Yeah.
so the figure on the left hand side, both of the figures are showing the trend.
Hmm.
But as you said, the left one is better in forecasting over the right one.
Right.
Right. Okay. Okay.
Yeah. Not. I'm not. I'm not meaning better in forecasting. Actually, the problem is that in the right hand side you won't be able to do forecasting.
Yes.
The left hand side you have a formula. Like you have a formula A plus BT, and
Yes.
suppose you put T equal to 1000. So that means at the 1000 day it will give you some value. That value may not be good, but at least you will get something. But in the right hand side you won't be even able to get any value. So that's the main problem.
Got it, sir.
Yeah.
Thank you.
Yeah. Now suppose you have used either this method of mathematical curve fitting or use the method of moving averages to calculate the value of the trend function. Then what is the next step? The next step is to remove the trend function from the data. and that is called the trend removal. And after the trend removal, the data that we are left with, we call it the detrended time series. So it is something like the residual in linear model for the regression problems. Like in regression problems, you remove the fitted value from the original observation, and that gives you the residuals. So similarly in time series also, when you remove the trend part from the original time series data, it will give you the detrended values. But how to remove it? I mean, the removing can be done in two different ways. I can subtract to remove this from the data, or I can divide. So which one to do? So at this point, I have to make certain assumptions, and I have to make some structural assumption for the underlying data. Now, how do I make this assumption? We'll discuss about that later, maybe in this class or maybe in the practical class. That we'll see that. But we have to make some structural assumption, and one such structural assumption is called classical decomposition of time series, and it is called the additive model under the classical decomposition of time series. And what the additive model tells, it tells you that if you take the trend function, if you take the seasonal function, and if you take the irregular fluctuation part, and if you add all of them together, you should get back the original data. So it is just like a hypothesis, or it's like a hypothesis, or it's like an assumption. Okay, it may be the case that your data is satisfying this assumption. For example, the picture that I have shown here, the assumption is being satisfied. On the other hand, there are a possibility that this assumption is not satisfied. In that case, this additive model may not be sufficient. We may have to work with something else. We'll see that later. Okay. Now, in this case, the additive model is satisfied. So now if I get the trend value, if I want to remove the trend value, what I have to do? I have to take this TT in the left hand side, and I have to subtract that from the YT, and that should give me the seasonal part and the irregular component part. You will see that. So can you see that after removing the trend part from this data, which we call by the name detrended time series. So after removing the trend, I'm getting it. So I'm calling it detrended. So these detrended time series look like this. And what is this detrended time series? This is basically this two part, the seasonal part and the irregular part. And so it contains a seasonal part, and it also contains the irregular part. So irregular part means the part that we cannot explain as seasonality. I mean, there may be many other uncontrollable factors that are playing their role. So those are included in the irregular component. Now, at this point of time, what should be our next goal? Our next goal is to determine the seasonality. So how do we determine the seasonality? So determining seasonality is simple, at least for this particular case. So you take the, so remember I told you that this is basically actually I'm showing you the air passenger data, data similar to that one. So this is basically a monthly data. So this is the observation for month of January for 1949. Then again, there's another observation for month of January for 1950. Then again, another value for month of January for 1951. Then another observation for month of January for 1952, 53, January of 1954, and so on. So you take all these values for the Januaries. So there are 12 such values because there are 12 years and 12 observation associated to month of January for this 12 years. Just take them, just add them up and divide them by 12. So that should give you the arithmetic mean of these values, and that is your seasonal part. So that is your ST function. ST, where T is T stand for the January. Similarly, you can do the same procedure for when T is for February, and then you can do the same procedure for T equal to March and so on. So that way you will get the ST function.
Sir, can you please repeat the ST once again?
Yeah. The thing is that once I have got this TT function, the next step, I want to calculate the seasonal part. Now, how do I calculate the seasonal part? Now, after detrending, after the trend part is gone, you see that the values for each January, they are more or less similar. So January for 1949, January for 1950, January for 1951, January for 1952, January for 1953, January for 1954, and so on for all the 12 years. So I'll take all those observations related to January, I add them up and then divide it by 12. So that will give me some number. I call that number as S evaluated at January. So suppose this is my S Jan. So that means the seasonal value at January. So how that is calculated? So you take this YT detrended time series for all the Januaries. So there are 12 such values for 12 Januaries for 12 years. So you just add them up and then divide it by 12. So that is how I'm getting it. And that should give me the S January.
So,
But is it okay?
so
Yeah.
So, sorry, sir, I wanted to ask one question. This
Yeah,
y
yeah.
y comma t minus t comma t. This is overall uh, depicting the detrend. Can you just, sir, explain what do these mean? So these mathematical functions, except from ST, I understood that.
Which one?
This, so this, for example, when you remove that, when you detrend it, sir.
Ah, right.
So yes, sir. This one, sir. This
This one.
So the previous screen.
Okay,
Yeah, this
I
one.
understand. Yeah.
So the equation that we are having is I understood the seasonality part. That the T comma bracket T part is the irregular part, sir.
This one, the small t.
No, sir. So YT is equal to capital
This
T,
thing, this thing.
small t.
Yeah,
Yes,
this is the irregular part, right? This is the irregular part.
plus the seasonality part, sir.
Plus the seasonality part plus the overall trend part. So if you add all of them together, that should give you back the original data. But this is your assumption. This is your assuming. You are making a structural assumption. There is no guarantee that your data will satisfy this assumption, and we'll see what to do in that case.
Yes, sir.
Okay. Yeah. So is it now clear how we are calculating the seasonality for January?
Yes, sir.
Okay. Now once you have got the seasonality value for the January, similarly you can calculate the seasonal value for February, for March, and so on for all the 12 months, and you see then ST will repeat. Okay, and that way now you got the value of the trend function, and as well as you got the value of the seasonal function. So you already have got the detrended value. Now you also remove the seasonal part from that detrended value, and this is called the detrended deseasonalized time series. So you have removed both the trend part and both the seasonal part. So both are removed from the data, and this is called detrended deseasonalized time series. Now, once you are getting this deseasonalized time series, according to our model assumption, what you are getting, you are left with actually the irregular part. So you remove this T part, you remove the seasonal part from the data, so you are left with only the irregular component part. Is it okay? So this is how the irregular component would look like once you remove the. So recall that this was our original data. I got the trend, I remove it. In the next step, we got the seasonal part plus the irregular component part. Then I estimated or determined the seasonal part and I remove it. And then we are left with this. So this actually gives us this IT, the irregular component part. So this is how the irregular component part could look like. And from now on, we'll work with this irregular component actually. Is it okay?
Sir, for seasonal, we have to remove seasonal Jan, seasonal Feb, seasonal March, seasonal April, like this.
Right. So seasonal, right. So seasonal March will remove when you are talking about the irregular component for March. Seasonal February will be removed when you are talking about the irregular component for February. It's like that.
So we will need to subtract the seasonal the summation or from every
Individually, not the
individual.
summation one, individually.
Okay, we will need to deal with every irregular component of every month.
Right, for every year, also for every year.
Okay.
So yes, since you are asking this question, actually this is very relevant. Suppose I am looking into the January for 1961. Okay. So suppose I'm looking into the January of 1961. Then at YT, I'll take the value of Y value at January 1961. I'll remove from that at the trend value of January 1961. And I'll remove the seasonal value of January only, because seasonal value, the year doesn't matter. Then suppose you are looking into the irregular component of January 1962. Then you will take the Y value of January 1962. From there, you will remove this trend value of January 1962, and you will remove seasonal value of once again the January, because January doesn't change. The seasonal value doesn't change from year to year. But the trend value will change, the YT value will change. So we have to keep track of that. Now, as I have told you that there is no guarantee that the additive model assumption would be valid. For example, the initial one that I have shown you, the air passenger data, it is actually doesn't satisfy the additive model assumption. In that case, we may have to work with a multiplicative model. It is called the, it is again a very popular model. It's called the classical decomposition with a multiplicative model. And in that case, we assume that the trend part, seasonality part, and the irregular component part, they form the data, but now not by adding them, but by multiplying them together, we are getting the YT. So in that case, how do we remove the trend part, or how do we remove the seasonal part? Now subtracting won't help us, but dividing the original YT data by the trend part and the seasonality part should return us the irregular component. So that is what we do in that case. For example, this is an example of a data set where the classical decomposition under the additive model is not being satisfied. Here we have to do the multiplicative, and we have to remove the irregular component. We have to remove the trend and seasonality by division, not by subtraction in this case.
Sir, I have a question.
Yeah.
Sir, how to decide which model to additive model to apply?
Right. Yes. Actually, very important question. Now, can you see that in this case there is a trend, and you also see there is a alternating seasonal behavior, but you can also see that the amplitude of the oscillation is also increasing. If you see such thing, then that implies a multiplicative model is true. On the other hand, suppose I go back to this model, this data. So there is an increasing pattern, then there is a seasonal alternating behavior, but you can see that the amplitude of the oscillation is not increasing. There is always a oscillation. There is an up and down, that kind of an alternating behavior is visible, but the amplitude of the oscillation, that is not increasing. On the other hand, in this case, if you clearly observe that, you see that as the time is increasing, as the trend is increasing, the amplitude of the oscillation is also increasing. And why this is happening? That means the trend and seasonal part, they are multiplied with each other. So that's why when trend is 3, it is giving us some value maybe from 205 to 405. And when trend is 6, it is giving me a value from 100 to 600. So that's why the amplitude of the oscillation is also increasing. So whenever you'll see the amplitude of the oscillation is increasing for your time series, you should always go for a multiplicative model.
Sir, can you give a slightly more understandable examples?
Yeah.
Like how would we know? I mean, how would we judge that?
suppose suppose I give you an equation of straight line. So suppose this is an equation of a straight line, e plus bt. And then suppose I give you another function gt, which is sine t. So that means an oscillatory behavior. Like that. So if I add up these two functions, ft plus gt, how would that look like? If you use any software and if you add this up, these two functions and plot them, the added function, so this will be a new function, then ut, you'll see it would look like this. Like this. On the other hand, suppose you are working with such a function that a plus bt into sine t. So your function is then a plus bt into sine of t, that kind of function. If you just try to see the graph of such a function, you'll see such a function would look like this. So just a minute. Like that. So the amplitude of the oscillation is also increasing. So whenever a periodic function is added with another non-periodic function, the amplitude of oscillation remains same. So amplitude of oscillation, by amplitude of oscillation, I'm just meaning this width. So this width is also increasing. On the other hand, if you are looking into the additive form, you'll see it would look like this. So that means in the additive form, the amplitude of oscillation is remaining constant. So based on that, you have to decide whether the additive model is appropriate or the multiplicative model is appropriate. So you have to judge that by looking into the picture. So that's why it is
Sir,
very important. Plotting the time
but-
series data.
Sir, but if we see the example, the trend is more clearly represented by the additive model, because if you see the first function, sir, which is the ft is equal to a plus bt, it is showing an incremental trend, and the sine trend is oscillating, sir. So when we do the addition part, sir, it is actually clearly showing what exactly were the original trends. But if once we multiply, it is not giving us a clearer picture.
Right. So in this case, it is happening because the seasonal part is taking the positive and negative values. Maybe the picture, it is giving you that impression because I have drawn the picture in this way. Maybe if I draw the picture in this way, then once again you will think differently. Now in this case, it still have a very clear-cut trend. That is all right. But at the same time, the amplitude of oscillation is also increasing. So I think
which is
yeah.
an additive model, sir.
No, it is a
No, it is a
multiplicative model.
Sir, how much increase in the oscillation we
Yeah.
will use the multiplicative model? Is there any clear-cut
No,
rule for that?
No. There is no clear cut. It's actually subjective. These parts are subjective.
Sir, how will this affect our model, sir, once the amplitude is increasing while using the multiplicative model, sir?
This will actually give you this may give you completely wrong inference and also give you very, very bad forecasting. Because something which is multiplicative, you are actually taking them to be additive. So definitely that will give you it's like your data is completely non-normal, but you are deciding your hypothesis using t-test.
Okay,
It's
sir.
like that.
Then how to pick, sir?
Sir,
So I mean,
yes.
you have to plot it, and based on that you have to judge.
Okay,
Like
sir. So
for
both
for for
both have.
for example, suppose for example there is very minute change in the amplitude. Okay, very minute change. Now again, what do I mean by minute? How much minute should be minute? Those are again the issue of debates. But if you see very small changes, then you of course go with the additive model. But as we have seen in the air passenger data, there is a substantial change, and it is clearly visible that amplitude is growing. Okay, in that case, you definitely have to go for a multiplicative model.
Sir,
Otherwise, you will
then
get
is it,
completely a poor kind of forecast. Yeah.
sir, then is it always good that we should go for multiplicative model?
No. In many a time, actually, it is enough to work with the additive model. And if it doesn't work, then you should go for a multiplicative model. And also, there is a way to transform a multiplicative model to an additive model. It's very simple. You just take the logarithm of your data. Suppose, of course, I'm assuming that your time series data is a positive value time series data, like count of something. So in that case, if your data is following multiplicative model, you just transform your data to log. Because if you see here that that if this is my equation, that then if I take log of ut, this is just simple property of logarithm tell us that something like that. So in that case, actually, if instead of working with the original data, suppose your original data was y1, y2, y yt maybe, or n, whatever, then instead of working with the multiplicative model for your original data, what you can do, you can work with log of y1, log of y2, and log of yt. You can consider this, and you can work with an additive model. That is also okay. Is it okay?
Sir, what will this logarithmic transformation achieve, sir?
The logarithmic transform actually convert the multiplicative model. So it will actually convert your data to a form so that you can work with an additive model. Suppose you don't want to directly work with a multiplicative model. So what you can do, you can transform your data to a form so that it is workable under a additive model. So that is the objective.
Okay, sir.
Okay.
And vice versa will also hold true? No.
Sorry.
Sir, vice versa?
Yes, in that case, suppose you are given an additive model and you don't want to work with an additive model and you want to work with a multiplicative model, then you have to do the reverse operation of logarithm. And reverse operation of logarithm means exponentiation. So you basically have to take e to the power something. So the exponentiation, you have to do the exponentiation in that case. So the reverse, the vice versa can be done also. But generally we don't do it. Generally we prefer to work with additive model. We never, if additive model is suitable, we never go to multiplicative domain, because multiplicative models are difficult to handle. So our tendency is always to bring into additive form. Okay.
So,
okay. Okay. Now, once we have got this irregular component, our next step is to calculate some more summary measures. One such summary measure is given by the sample autocorrelation function, or SACF, or it is also has another name. It's called correlogram. Now, This is the working formula of correlogram. Let me just explain what do I mean, what is the objective of correlogram or the sample autocorrelation function. Now, it actually calculate that. So this is the detrended deseasonalized data. Now, the correlogram or the sample autocorrelation function actually calculates how much today's data is correlated with tomorrow's data, or how much today's data is correlated with day after tomorrow's data. So it will actually calculate the correlation of different lags. So let me explain it. Yeah, so it actually calculates. So how do I calculate correlation or sample autocorrelation function of lag 1? So so first I'll create a data vector in this way. So I'll put the today's value here, and I create another vector y, and I put tomorrow's value there. Then I put tomorrow's value here, and then I put day after tomorrow's value here, and I keep on doing this. And then you just calculate simple correlation between them. So it's like we already know, if we have such a data set, such a data set, a bivariate data, we can easily calculate correlation by using software or by using the formula. So similarly, you can calculate the correlation between this x and y. So that actually give you the sample autocorrelation function for lag 1, because it is actually giving you how much the day, one particular day and the next day is correlated. So it actually gives, it is given by this particular value. Okay, how much the number of patients, which is of course a variable on a particular day, and the number of patients on the day after that particular day, how much they are correlated. Of course they are correlated. That's what the whole point of discussion of time series analysis, that today's observation has some correlation with tomorrow's observation. So I need to assess, I need to quantify that correlation, and that is given by this sample autocorrelation function of lag 1. Now this will give you the sample autocorrelation of lag 1. What about the sample autocorrelation of lag 2? And what you expect, that today's observation has some correlation with tomorrow's observation, but today's observation will definitely also have some correlation with day after tomorrow's observation. But since now they are quite far apart, so the correlation value should decrease. So that means if we calculate the sample autocorrelation function of lag 2, in generally, it is expected that this sample autocorrelation of lag 2 value should be lesser than sample autocorrelation of lag 1. In generally, it is, there is no guarantee of that, but in generally it is expected. This is a natural behavior, that today's observation is more correlated with tomorrow's observation. On the other hand, if we look into today's observation and the observation after 5 days, definitely that will also be correlated, but the correlation will be less. In an intuitive manner, this is understandable to us, right? Now, how do we calculate the sample autocorrelation of lag 2 in this case? So what we'll do, we'll take this. We'll take this. So 1, then with 3. 2, then with 4. So there is a gap of 2 days between all of them. And then I calculate, once again use the usual formula of correlation, and that will again give me some value. I call that sum value as my sample autocorrelation of lag 2. And in this way, I can calculate autocorrelation of lag 1, lag 2, lag 3, lag 4, lag 5. In generally, this is just a thumb rule that if your time series is of length 100 or 120, you can calculate autocorrelation of lag up to 40, 45. And you don't need to go beyond that. In generally, it is not needed. Okay, so this is just a thumb rule. Now, if there is no more question, I'll go back to the slide.
Sir, I have a question. Why do
Yeah,
we
yeah.
need to see the autocorrelation? I mean,
Yes, suppose you calculate the autocorrelation of lag 1 and you see it is very small. So that means whatever the number of dengue patient today we have, that has very less correlation with number of dengue patient on tomorrow. So that means today's data is almost like independent with respect to tomorrow's data. So that means, in other words, it is less of a time series data, and we can use the usual classical statistical method like t-test and other kind of technique to work with that. Because the salient difference of time series data with the usual data is that the 2 consecutive days should have some meaningful correlation. On the other hand, if you get a very less value for that, suppose you got a very small value like 0.001, so that means today has no correlation with tomorrow. So it is really not a time series data, although it look like a time series data, but it really not a time series data. And we can use the usual classical statistical technique for working with that kind of data. We don't need to learn any time series analysis for that. So that's why we look into this correlation.
And then it is up to the researcher to decide how much lag period is to be
Right,
taken.
it is
while
right. It is up to the researcher. In generally, if your time series is very small, then you cannot go up to lag 40, 30, 40. Okay. Suppose your time series is time series on yearly data and you have data for 60 years. In that case, you cannot go up to lag 40, 45. Okay. Then you will get unreliable estimates. So in that case, you may have to settle with lag 20, 25, or only that. On the other hand, suppose you have a large enough time series, like a time series of size 100 or 150 or 200. In that case, you can easily go up to 40, 45, but it is up to the researcher, up to how far lag he just want to check. But in generally, it is expected that beyond lag 40, there won't be any correlation. Like what is today's number of dengue patient and what is after 40 days, what would be the number of dengue patient? These two numbers should not have very much correlation. At least from our intuitive thinking, we can understand that. So that's why generally we don't look beyond 40, 45. But of course, it depends on the researcher, and it also depends on the particular data set in your hand. There may be some speciality in the data set where you may have to look beyond those 40, 45 lakhs, which is the thumb rule.
So what is the threshold? For example, when we learn simple linear regression, the R value is, so we have these demarcations. If it is point from 0.0 to 0.25, it is weak correlation. 0.25 to 0.5, it is moderate, and then 0.75 to 1, it is strong. 0.75 to 1 is strong correlation. Do we have something like this here also?
No. We don't have any such thing, because you see that these correlations themselves are different kind of thing. I mean, you have, it's like you have 40 such different values of correlation, and each has different nature. Like if you set a threshold for the correlation of lag 1, that cannot be a threshold for correlation of lag 20. You can understand that, right? Because at lag 20, correlation will anyway will be very small. On the other hand, lag 1 correlation may be quite high. So if you set such a threshold for lag 1, that threshold is not going to work for the correlation of lag 20 or lag 10. For lag 10 or lag 20, you have to set a separate threshold. So that means you need to set so many thresholds for each of the different lags. So actually there is no such threshold. At least not in common use. I mean, It may be some specific work someone may come up with such threshold, but there's no such popular kind of recommendation of thresholds like the usual correlation.
But sir, that autocorrelation should be statistically significant.
Right.
Okay.
So
okay.
for doing that, we have to perform testing and check the p-values. Okay.
Yeah, at whichever lag it may be there, but this has to be statistically significant.
Right. These have to be definitely, yeah.
And
Definitely.
then we have to identify that lag, and based on that lag, we can build the future model.
Right. Yeah.
Okay.
So then that would be the part of the inferential statistics part.
Okay. Thank you, sir.
Yeah. Okay.
And if it is not statistically significant correlation on any lag, then
then you should not do
consider this for time series.
Then actually you should not use time series analysis for that.
Okay.
Sir.
Okay. Yeah.
So does like a disease incubation period has anything to do with this determining the lag period in the scenarios?
Disease incubation period. I'm not sure about that. I don't think that has anything to do with this correlation part. I mean, that may have something to do with the behavior, changed behavior in the trend part, but I don't think with correlation part.
Rather than incubation period, you can say that what is the bacterial or viral load, day-wise bacterial load, day-wise viral load, and then correlate that function and determine the time series function like that.
Yeah, maybe, but but I think these are some of the more medically specific to medical science. So I'm really not very much aware of that. Yeah.
Okay, sir. Thank you.
Yeah. Okay, so this is the formula. I have already told there, but this is the mathematical formula for calculating the sample autocorrelation function. But see that there is a problem with sample autocorrelation function, that when you calculate the autocorrelation, so when you calculate the autocorrelation, when you calculate the sample autocorrelation function of lag 1 or lag 2, there is a problem that when you calculate the autocorrelation between lag 2, suppose you are calculating the autocorrelation with today with the day after tomorrow. So there will be some correlation, but some part of that correlation is because of the tomorrow. So it is like so if y1 and y2 have some correlation, some part of that correlation is because of the intermediate point y2. Okay, so it's like a common variable. So on the other hand, if we are really interested in knowing the true autocorrelation between y1 and y3, so we have to partial out the effect of y2 from there and calculate the correlation. So that is what gives us sample partial autocorrelation function. So just like we have discussed about the sample autocorrelation of function, similarly we have a concept of sample partial autocorrelation function. Let us consider another example.
So what is the difference between that sample
Sup-
autocorrelation and partial autocorrelation?
Right. Suppose I want to calculate the sample partial autocorrelation function of y1 and y4. So that means if you directly calculate the sample autocorrelation function between y1 and y4, there may be some part of dependency because of this common part y2 and y3, because y1 has some correlation with y2, y2 also have some correlation with y3, y3 has some correlation with y4. So that's why y1 has some correlation with y4. So part of this correlation between y1 and y4 is because of this common part, this y2 and y3. So if we really want to know the true autocorrelation between yn and y4, what we have to do? We somehow have to calculate the autocorrelation between yn and y4, partialing out this y2, y3. So it is like, then, for example, this is like this. So suppose this is y1, this is y4, this is y2, this is y3. Then again, this is y2, this is y5, this is y3, this is y4. And suppose if we keep on writing in this manner, we finally get yn minus 3. No, not n minus 3, n minus 4, yn. No, sorry, it's yn minus 3. Yeah, yn minus 3, yn, this is yn minus 2, this is yn minus 1. And then previously what you are doing, you are calculating to get the sample autocorrelation of lag2, you are calculating just the autocorrelation between x and y. Now what you will be doing, you will be calculating the autocorrelation between x and y, but partialing out the effect of this two. So that actually gives us the sample partial autocorrelation function, and that will actually tell you the true correlation between this x and y, partialing out the effect of the intermediate variables. Is it okay?
Sir, is it the correlation between y2 and y3, or is it the combination of the correlations between y1, y2, y1, y3, and then y4, y2, y4, y3?
Everything. When you partial out, all the intermediate effects are going out from
So
the
it is a
y1.
combination of all the possible combinations of
Right. All the possible combination of all the intermediate days that will separate out the 2 days on which you are calculating the correlation.
So that gives us the true correlation between the end variables.
Right.
Right. Okay. Thank you.
Sir, my
Yeah.
question is, what is the advantage of calculating the correlation between the two end variables rather than calculating y1 and y2, say?
Yeah, actually, this will be useful while deciding the model for the data. I mean, there are some models like ARMA model or AR model. Now that AR model, in that case, when we try to decide the order of the AR model, we actually decide it by looking into the sample partial autocorrelation function. So there was one question from one of our participants, that how do we decide the order of MA in ARMA model? So there is one to decide if you are working with an not an ARMA model, but if you work with a MA model, then the order of the MA model can be decided based on the sample autocorrelation function, this one. Okay. On the other hand, if you are working with an AR model, then the order of the AR model can be decided by looking into the partial autocorrelation function, and that is the utility of calculating the partial autocorrelation function. Now you can see in this picture that here in the left hand side we have calculated the sample autocorrelation function. This is the autocorrelation of lag 0, which is always lag 0 means the correlation with today. So that is always 1. That is +1 all the time. So that's why you can see it is +1. But this is today with tomorrow, then day after tomorrow. As I have told you that it is most often it is expected that the correlation will decrease. That is what we can expect. However, you will see that it is going after maybe lag 0, lag 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's like so much. And there is a line. This line is actually obtained by some testing procedure. And beyond this line, anything that falls below this line, we consider them to be 0. So anything that is inside the line, we call them, we'll assume that this is basically 0 autocorrelation. So that means up to lag 13, 14, we are getting correlation. Actually, there also we are getting some correlation, but for the time being, let us ignore that. But then also we are getting correlation up to lag 13. So that means for this particular data set that I'm considering, today's data has some correlation with the data at even after 13 days. But is it really true? Is it true that today's observation is really truly affecting the whatever is happening after 13 days? No, that is not true. That is evident when you calculate the partial autocorrelation function. You'll see once again, you'll see after only lag 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. After lag 10, everything is beyond 0. So that means maybe after lag 8 or 9, your actual correlation today actually doesn't really have any effect after day 10 or 11. But still, you are seeing that because of the intermediate commonalities between them. So, am I making sense? The difference that we are conveyed through the sample autocorrelation function and sample partial autocorrelation function. So it is actually measuring the true effect of the data for the tth day on the data on t plus hth day.
Sir, H is what?
H is the lag. Basically, H is the lag.
And T is the
T is to suppose we are looking in the tth day and how much that is affecting t plus 13th day. Like I was giving that example, that is it affecting the observation after 13 days? So in that case, H is 13 basically.
Okay, sir. Thank you, sir.
And what is there on y-axis, sir?
In y-axis, you have the correlation value. So after maybe 13, 14 lag, there are two straight lines. These two straight lines are actually obtained using some test statistic, and anything within that straight line would be considered as 0.
Okay, means after 10 or 13, there is no correlation.
Right,
up to,
there is no
up to 13
correlation.
there is correlation.
There is correlation. Actually,
Similarly, for partial, there is after third. There is
no, not
correlation.
after third. Actually, there is a slight value, maybe after 9 or 10. I think.
Okay.
But still, it is very, very less. I mean, you can see it is almost falling on the line. Anything that is falling on the line, that you can safely ignore. So in that sense, you may say that after lag 1 or 2, it is basically going to be 0. So truly, today only have effect up to 2-3 days. It's like that.
Sir, so
Yeah.
these two lines, one which is above this 0, sir, above, and one below. So this is the window in which the correlation SACF should lie, sir. Is that
right?
sir?
Right. So within this window, if your correlation lie, you consider them to be virtually 0, because since this is a real life data, nothing can be exactly 0. I mean, it's not a theoretical object, it's a empirical data that comes with lot of errors and lot of things inside it. So you can never expect that to be exactly 0. So what statisticians have done, they have derived some test procedure, and based on that, they have derived a window such that within that window, if these values fall, you can call it to be 0. So it may be a partial answer to the question you are asking, that are there any threshold that if the correlation value lie between these two values, we call it medium. If this lie between this threshold, we call low. So it is like a partial answer to your question, that if your correlation value lie between these two thresholds, we call that zero correlation. But of course,
Sir,
it's not a full specification.
So, sorry to taking a tangent, but sir, when you were explaining, you said that true time series data between one point and other point, there will be some correlation. That is why it is called a time series data, right, sir?
Right.
So I'm little kind of not clear, sir. You said zero correlation. I mean, what is that?
Zero correlation means this time and the time series, the value that is occurring after 14 day, these two have no correlation. But of course, if you take this the second day and that may have correlation. So today and the 14th day doesn't have any correlation, but tomorrow and the 14th day may have correlation, or the uh, 5th day and the 14th day they may have correlation. That I am not negating. What
Okay,
I'm
sir.
just saying that from today, if you start counting, the strength of dependence will extend only up to day number 12. But beyond 13 and
Oh,
onwards, it is kind of, it
so,
become negligible.
sir, so if
Yeah.
you see the graph on the left side, sir,
Hmm.
and you see the first line on the day 0, which extends right, if you plot it against the y-axis, it touches the uppermost extreme, sir.
Which is 1 plus 1.
Yes, sir. So that is the correlation coefficient on day
Today
0,
with
sir.
today. Today with today.
With today.
So that is lag 0. If you see that, you'll see a 0 written here. So that is lag 0. Lag 0 means today with today. So that will
And then,
definitely be perfectly correlated.
yes, sir. And then
Sir,
it is
is
lag.
the sorry to interrupt. Is the x-axis the lag?
Yes, x-axis is lag. So
Okay.
you'll see that they have plotted it up to 45. As I was telling that in general, it's a thumb rule to plot it up to 45.
Yes, sir.
So this is a
So, sir,
graph of correlation versus lag, is it?
Right.
So what is the significance of the bars going negative after like after like lag, I can't read it, around 20, or it's going negative?
Yeah, 30. Yeah, right, around 30. It is
What,
becoming negative.
what is the significance of that?
So it means that there is a negative correlation with today and the value that is occurring after 30 days. So if today is too high, today is too high, then or increasing to tomorrow, then at around that region, it must be decreasing. It is something like that.
Thank you, sir.
So it may happen that since it is increasing today, maybe some kind of intervention have been applied, and that we see the effect after 30 days. Maybe I'm just saying some in a more vague sense, and because of that, maybe there is a negative correlation.
sir, what is this graph called, sir?
What is this?
This particular this picture, sir,
This is,
graph. What is this?
this is called correlogram. The left hand side is called correlogram. And right hand side doesn't have any name. This is basically you can call it partial correlogram, but it is not a standard terminology.
So basically, sir, for this particular day, we have plotted the correlation for the subsequent 40 days, sir.
Right. Not for this particular day. This is for in general. It's not like I am assuming today to day after 13, but I am saying that today to day after 13, starting from today, if I consider the day after 13, or if I'm taking 10th day and 23rd day, that is also okay. So it's a gap of 13 days. It's not, the T is not important. I mean, here this T is not important. I mean, you cannot fix that T. So then there will be too many correlations. Like for each lag H, you will get correlation, as well as each different value of T, you will also get correlation. Then it will become too many things to deal with.
So, sir, if we take a point, for example, on day 10, and we see the line which is crossing the line which is just below 0.20 and is reaching right just short of 0.40, sir.
Right.
And then compare that with on day 20, sir, which is going below, sir.
Right.
So how do I interpret this finding, sir?
The find you can say that today's or not today, I should not say today. Whenever I'm saying today, it's like emphasizing on the particular value of t, but it is just telling you that if you are looking the number of patients on a particular day, and after maybe 12 day, they have a strong correlation like 0.4. It is telling like that. So if it is quite high on today, so it is expected that even after day 12, it would be relatively high. On the other hand, at day 20, it is on the negative side, but note that whenever something lies within this threshold, it is practically we consider that to be 0. So in that case, we can assume that whatever is number of patient on today and whatever is the number of patient on the 20th day, this two has no connection. They are completely independent of each other. They have no link between them. It's like that.
Okay, sir. Okay, sir. Thank you, sir.
Okay. I think maybe we can stop, if we can stop for today, and then I can continue this on the next class. So I think that would be a better idea, because this part would require some more time, this time series models and the forecasting part.
Yes,
So will
sir.
that be okay with everybody and the organizers? So
Yes, sir, it is okay with that. Today is almost 10, so we
right,
need to, sir, also end the session. So with your
yeah,
permission, can we, sir, end today's session, sir?
okay. So then we'll continue the thing on the next class.
Because if we need 1 or 2 more sessions after the scheduled dates, we can add on, sir. That is not a problem.
Okay, fine.
Okay, then with permission of sir, we can end today's class. Thank
Yeah,
you, sir, again for this elaborate discussion and helping every way possible to us. We will meet again the day after the next day, that is 17th.
yeah.
So till then, everyone, good night and thank you, sir, once again.
Thank you to all.